Welcome to the final lecture for Fluid Mechanics, CAT 374. I know you guys are so excited for this to be done. Anyways, we're going to finish up the computational fluid dynamics that we started last week and we will give a couple of examples and we will discuss more or less some of the things that we'll talk about for the final, since this material will be on the final. So first and foremost, let's start with a spiritual thought. This is from Elder Russell M. Ballard. He said, "Let me repeat and emphasize that point. You will lead the church in 20 to 30 years from now. Some of you will serve as bishops, stake presidents, mission presidents, primary young women and relief society presidents, and temple presidents and matrons. Yes, within the reach of my voice tonight are those who will most likely become leaders in communities and nations of the world. There will be those who will be members of the general women's presidencies, or even a general authority 70, or perhaps a member of the quorum of the 12 apostles." To me, this is an amazing reminder of the great potential that each of us has and the love that our Heavenly Father has for us. So keep that in mind as you move forward from this point on, that we are those who the Lord will hope to be able to rely upon in the future. So let's look at the roadmap. Right now, we have covered everything on this map, and again, just like last week, this is the final topic, computational fluid dynamics. So let's look a little bit at what we talked about last time, and let me correct the mistake that was inherent in the last lecture. So we had started with this 1D pipe flow, and I had mistakenly maintained del squared u del x squared, when really I should have maintained del squared u del y squared. That was a mistake in the notes that I did not catch, nor did I correct. So those of you who are confused, you're correct. It's not a fully developed profile, but we're looking with respect to time for the development, not for location. We're going to be at a single spot, a single slice in the pipe that doesn't move. So therefore, this term is indeed zero, because we are not moving down the pipe. We are looking at how that develops as we begin to have flow in the pipe. So in the future, we will be using del squared u del y squared. We came up through our simplifications with this expression. Again, this should be del squared u del y squared. I've corrected it in the slides that we'll look at in a minute. And we divided up the pipe diameter. This is from top of the pipe to bottom of the pipe into different nodes or different points that we're going to be analyzing. And we thus came up with an expression for the double derivative. Okay? So that's what we had covered last time. So let's come back to that. Again, this is the correct equation. Del u del t is equal to mu over rho times del squared u del y squared minus 1 over rho del p del x. Okay, we created the grid points across the diameter of this pipe, or we could perhaps consider it a ubiquitous flow channel. And then what we did is we approximated the second derivative numerically. You remember we went through that process of taking the derivative of the derivative at the different points, and this is the expression we came up with for the double derivative at point I. Okay? Then we plug that back into our original equation right here to come up with this expression. And you note now that we include as a partial derivative, instead of just del u del t, we have del u I, meaning that this derivative is evaluated at every single point that we picked across that pipe diameter. Okay? And then as our boundary conditions, we use the no-slip condition, or in other words, at the first point, the point that is the wall at the top of the pipe, the velocity is 0. And then for the nth point, the final point, or the wall at the bottom of the pipe, the velocity is also equal to 0. So the no-slip condition gives us our boundary conditions of 0 velocity at the top and bottom walls of the pipe. And that means this is converting the PDE that we originally had up here into a series of n minus 2 coupled ordinary differential equations. Coupled because if you look here at the format, every ordinary differential equation for I also has a corresponding I plus 1 and I minus 1 dependence. So every point of velocity depends on the velocity on either side of it. Okay? So that's what we had done last time. So now, how do we consider the time dependence? Now we'll want to solve these ODEs, and to do that, you can either use your favorite ODE solver. There's many packages available that can do this, including MathCAD and Python, SciPy and NumPy. Or what we're going to do is we're going to look at solving it using the explicit Euler method. Okay, so in other words, what we do is we recognize that for the derivative of some function, in this case we're taking the derivative of velocity with respect to time, or how that velocity changes with time, that's equal to some function of u. So what we can do, we can approximate that as saying that u for the n plus 1 time step, or the next time step that we're interested in, minus u for the current time step, or u of n, divided by the time step increment size is equal to the function of u at time step n. In other words, we can solve this expression here to say that the velocity, or the solution to our differential equation here at time step n plus 1 is equal to the solution at the previous time step plus the time step interval size times the function right here, the function at time step n. Okay? So for our particular equation, what that means is that u at time step n plus 1 is equal to ui at n plus the time step interval times the function. Okay? So that is, in essence, what we can do for solving this 1D unsteady flow problem, or any other flow problem that is a PDE that we can then discretize, or in other words, break into tiny pieces. And then, once we've broken it into tiny pieces, we can then approximate solutions for each of those pieces, add them up together, and we have coupled ordinary differential equations, and we can solve them using an explicit Euler. Now, as I mentioned before, there's challenges. This has varying degrees of accuracy depending on the numerical methods or the solver that you use. And in this case, the Euler is a simple and easy solver, but it doesn't necessarily have the most promising or accurate results for complex geometries or other compounding factors that I'll talk about in a little bit. So let's actually look at the solution here in Excel. So this is an Excel example of this exact problem, a 1D unsteady momentum equation. Okay, we're going to use the explicit Euler central difference, meaning we're taking the derivatives around either side like we did before. It's a first-second differential equation in time and a second-order differential equation in space. Okay, so what we can change is the boxes. dpdx, or the yellow highlighted boxes, dpdx is the pressure drop per length, okay, and it's in pascals per meter. N is the number of nodes across the pipe, okay. D is the diameter of the pipe. In this case, we want a 1 meter pipe. That's 13 nodes. dx is the interval between the nodes. And in this case, it's simply the diameter of the pipe, C10, divided by n minus 1, or 12. So this is 1/12 of a meter. That is dx. Okay. dt is the time step interval, in this case 1,000 seconds. Rho is the density of water, standard 1,000 kilograms per meter cubed, and mu is the viscosity of water. In other words, 0.001 kilograms per meter per second. Okay? So we're going to come up with this term d, which is simply dt divided by dx times mu over rho. Okay? Remember, from the equation here, we're just coming up with this expression. I put dx in the notes. It's actually the dy, as I mentioned at the beginning of this lecture, so don't be confused by that. So d on this Excel sheet right here is simply the numerical value of this expression. Okay? So then what we do is we've written out the index, or I, for every point. You notice I1 was the point at the top wall. Notice what the velocity is across the entire approximation. And then IN, or I13, or I13, yeah, that is the position at the bottom of the wall. Notice again that the velocity is 0 all the way across, since the top and the bottom are subject to the no-slip rule. Okay? And then for the position, we simply note the distance, the numerical distance from the top to the bottom. So the bottom is more or less 0 meters all the way down to the bottom, which is 1 meter in diameter. And then we start by initializing the property. The initial condition is that the flow, the velocity u, is 0 at every point. Okay? Then's where it starts to get interesting. At the next time step, that's the initial time step, t naught. At time step 1, we recognize that this is going to be 0 all the way across. We simply equate this to the previous step. In the middle, however, is where we begin to apply our differential equation. Okay? So if we look, didn't want to do that, just a minute. So let's shorten this window a little bit. If we look at our equation, we start off by saying the velocity at the current time step, or in this case, if we have the current step as time 0, we're trying to solve for t1. So t1, the velocity at t1, or in other words, u of n plus 1 is equal to u of n. So we indicate that the velocity is equal to, first and foremost, g7, which is u of n, plus dt dx squared times mu divided by rho. In other words, this right here, same as d we put right here, but this time we're explicitly writing out dt del y. I really should change that because dt is confusing, or dx is confusing. Let me change that really quick. Okay, so when we look at this, we have our ui right here. We have the coefficient to the derivative right here. We have the derivative approximation right here. And then we have the final term, dp dx times dt over rho. Okay? Because remember, we're multiplying both by delta t. I neglected to put the delta t in this term, my mistake. There should be a delta t over the rho here. So literally, this is what we do in order to determine what the velocity at time t1 is once we know the velocity at time t2. And we use that for every point here along this axis. Okay? You see how that works? And now, the dependencies of points refer or take into account in this derivative approximation. You notice that we have g8 at time 0, g9 at time 0, and g10 at time 0. So now if we go to the next time step, we have the same process. Now we're trying to determine the u at t2. So in other words, u of n plus 1 is now t2. U of n right here is equal to the u at t1, h7. We have the same coefficient evaluated right here. We have the same derivative approximation here using the surrounding points. And then we have the same pressure gradient driving term. And we just repeat that for every one of these steps. And then for the next time step, you'll notice initially this profile is fairly flat. But in time, as we progress along the time steps, it gradually begins to curve out and become the parabolic shape that we all know, until eventually we can see quite a large distribution, an order of 3 in magnitude from the second to the last point all the way to the middle, until we eventually will reach a quasi-steady state point where you notice every value is converging close to 0.0051 as the value. Okay? Now if we want to plot this out as an evolution in time, you can see this is the first initial condition, and as we pass further time steps, you can see that this profile at that one slice in the pipe begins to develop until we have the fully expected laminar profile in the pipe. Okay? So I posted this file online, and you can use this for your reference, but this is how you would numerically solve. This is a hand numerical calculation for a 1D unsteady momentum equation analysis. Okay? This is what we do for a Navier-Stokes equation that couldn't simplify into really stupid simple solution, but nonetheless is reasonable enough that we can come up with a numerical approximation. Okay? So that's kind of how you can do a first order differential equation. You can also do 2D, two-dimensional analysis using CFD tools, using the numerical approximations. Okay? This is very similar to doing it in 1D. Remember that in one dimensions, we have these 3 points, and we use the derivative based on the difference between all 3 of these points to find the second order derivative. Okay, so you can see that expressed here. So if we do it in 2D, we now just simply have to substitute the y derivative as well as the x derivative. So for the y derivative, you're going to find the difference between 3 values in the x direction. And for the y direction, you're going to be finding the difference between values in the y direction. So we simply use both of these expressions, just like we did on the previous example with one dimension. In both dimensions, combine those together in order to substitute the equation. Okay? So what we're going to do is we're going to end up with 2 differential equations, or PDEs, with respect to time. We have 2 differentials with respect to 2 PDEs with respect to time, and then we're going to convert those into 2 series of coupled ODEs, one with respect to x, one with respect to y. Remember, u connotes the x velocity, v connotes the y velocity. Okay? So, in this example 2, we're going to look at a 2D unsteady laminar jet, or a jet of laminar fluid flowing into a quiescent fluid. We'll have 3 equations and 3 unknowns. We'll have the velocity in the x, we'll have the velocity in the y, and we'll have pressure. We start with the continuity equation, which could also, remember, shorthand form, be expressed as the gradient of the velocity vector is equal to 0. Okay? We're also going to have the y momentum balance, the x momentum balance, and the y momentum balance. This x momentum is basically going to be our u equation, and this y momentum balance is basically going to be our v equation. So then that begs the question, if we have 3 equations and 3 unknowns, what's the p equation? We can get the p equation by taking the gradient times the momentum equation, and then inserting the continuity equation. Lots of algebra. Basically, what we end up with is this expression here for the pressure equation. Okay? And then what we do, just like with the 1D example, we discretize in space, and then we use the Euler approximation to discretize in time, and then we develop our boundary conditions. And the boundary conditions are going to be very similar. We're going to say that u is equal to v is equal to 0 at the wall, or if it's a moving problem, then u is going to be equal to v, which is going to be equal to v of the wall. Okay? And then in this case, we're going to have inlet conditions, where u at the inlet is going to be some defined velocity in, and v at the inlet is going to be some defined velocity in. At the outlet, we don't know anything about them, but we can express that the derivative is equal to 0 in both cases, because it will have the maximum velocity. Okay? One of the big problems we can experience is that at the outlets you can actually have recirculation flow. You can have flow from outside the problem coming back in if the pressure drops below the stated pressure at the boundary. And so what we have to do is locate those further downstream in order to prevent recirculation. In other words, make the boundary larger than the jet so that you don't have pressure gradients bringing flow back in. So I have an example of this using MATLAB online. I'm not going to take the time here to go over it explicitly, because it will be the same as the 1D problem. Although I do recommend, as part of your optional homework, if you're so interested in preparing for the CFD portion of the final, that you go over that code in MATLAB and make sure that you understand it. Okay? There's some other issues that we experience, okay, when we're doing CFD. For those examples I just gave, we use water, so that they were incompressible flows. However, as you remember from our compressible flow lecture, when these flows are compressible, we introduce a new complication that makes things dramatically more difficult. First of all, is that the limit of speed for a compressible fluid is sonic velocity when you are working with a typical nozzle. Well, sonic velocity is much faster than the general flow of the rest of the model. So what we have to do is we have to create time steps that are small enough that we can capture the speed of sound. What do I mean by that? Well, you remember, if we're breaking up the problem, let me bring this over here so I can re-illustrate. Sorry, it's a little difficult when I can't actually draw on the board. When we divided up this problem into these different steps, let's say we have these steps moving in the direction of flow. This is node 1, node 2, node 3. Well, if we're moving at the speed of sound at a certain point in our model, that means this flow is moving from here to here to here at a very high speed, the speed of sound. If our time step is too large, then that means the flow can move from this node to this node and skip over these two in one time step. And what that does is it introduces error because we don't know what's actually happening in these steps because it's skipped over completely. So when we're dealing with the speed of sound, we actually have to shrink the time step small enough that at no point will the fluid move over an entire node and pass an entire node. We have to make sure that every node is accounted for. So we have to have very small time steps so that even though the fluid is moving very fast, we capture every movement within the node. So that being said, compressible flow, just by nature of having the additional time steps, becomes much, much more expensive. In addition, as we talked about with compressible flow, you are converting energy into the internal energy of the fluid. You're changing the temperatures, you're changing the reference pressure and temperature. Remember, we dealt with P star and T star and the thermodynamics of the fluid. Because of that, we explicitly need to use an energy equation. And finally, we need some kind of thermodynamic expression for the gas. In this case, we have the ideal gas law. But this means we go from having 3 equations and 3 unknowns for the 2D problem, all the way to having 5 equations and 5 unknowns. So this makes the problem dramatically more complicated. So incompressible flow takes even more time and is a little more difficult to resolve than compressible flow. Finally, as chemical engineers, we will often want to deal with reacting flows. This is actually Dr. Lidnell's specialty. He deals with combustion in flows, or in other words, reacting flows, where the coal is combusting while flowing, and so you have to deal with additional reactions to balance each particular species that will be being created and destroyed. Think of what you did in 273, where you're balancing across the different species. Here you're going to be doing that while calculating the fluid properties. So this can get quite complicated and is a field of specialty in and of itself. And if you're interested in this, then Dr. Lidnell can give you a lot of details and you can work with him and do some really interesting things in evaluating CFD with reacting flows. Okay? So now we talked about laminar flow for these examples. We did that specifically because, as I mentioned earlier, once you get into the turbulent regime, you have an additional item of complication, and that is, how do you deal with turbulence? Remember, the whole point of the Navier-Stokes equations of this differential balance is to be able to say at every point what the exact three-dimensional properties of the fluid are. So at any point you could say exactly what the velocity is. Well, the problem is with turbulence flow, remember, we have all of these sub-eddies and these smaller vortices, this chaotic flow within the main bulk flow of the fluid. So although the average velocity is moving downstream at some average velocity u, if you're looking at any given local point, there's going to be some velocity in the x direction, in the y direction, in the z direction, and that changes not only with space, but also with time as the flow evolves. And this turbulence, this chaotic motion of the fluid on a subscale level is very, very difficult to deal with. So we have 2 options. The first option is we can actually explicitly resolve the turbulence. We can make the time steps so small and make the equations so precise that we actually include this turbulence in the flow itself. That's called resolving the turbulence. This is extremely computationally expensive. Okay? The other option is that we can come up with some approximate model, either empirical or theoretical, for the turbulence and model that separately. And this is most often what is done. Okay? A few other issues is grid quality. Depending on the complexity of the geometry, most commonly we use the various zero-dimensional volumes for these analysis rather than points. And if you have a very complex shape that you're trying to model with CFD, creating a grid that has a good quality can be extremely difficult. So you have to be aware of the quality of the grid. Make sure that none of your cells are really skewed or twisted or shaped poorly to give bad results. Also, the types of grids and diffusion models are very important. A structured versus unstructured grid. A structured grid is described in the book, but basically what type of shape you have, whether it's an ordered model that has the same points at the top and the bottom of grid, or whether it's less structured where you have a different number of points at top and bottom with different shapes. Also, you can deal with different shapes within the grid. You can have tetrahedrals, you can have prisms, you can have pentagons, you can have hexagonal cells. There's a wide variety, and this is an entire field of study to determine what types of grids, what types of discretization, what types of volumes will be best in terms of giving highest accuracy with the lowest amount of time. And a lot of these details are given in chemical engineering. Oh, I didn't even include the number right. 541. That's the numerical methods class that is taught by Dr. Linnell, and I highly recommend that class as being one that is worthwhile if you're interested in learning how to do numerical solutions to problems. I always tell people this is like having superpowers, because if you can solve partial differential equations by discretizing them, even if you don't use a full CFD, if you just use a hand calculation method, then you can come up with answers to problems that a lot of people cannot. And in fact, this is, if you're interested in grad school, one of the best tools you can have going into grad school is the ability to do this, because in grad school almost certainly you'll come up against partial differential equations that you cannot solve analytically, but with a little bit of work you can come up with an approximate solution using numerical methods. Okay? So again, we talked a little bit about turbulence. Here's the problem. Remember when we showed the boundary layer, and we showed that you had to have two different length scales. One very small length scale to represent the thickness of the boundary layer, and one very large length scale to represent the length of the plate, or the length going along with the flow of the boundary layer. That same thing applies in turbulence. You'll have a very big difference in length and time scales. The length scale that's largest will be the general bulk flow flowing down the pipe. But in terms of the turbulence, you could have very, very tiny eddies that don't even show up on the larger length scale. And same with the time scales. Some will be spinning or moving or dissipating much faster than others. So it's very difficult to capture all these in one model because of the very large difference in scales, going all the way from fractions of a millimeter to meters. Okay? And if you were to get enough grid points in order to capture all of these lengths and time scales, then you would see a huge model that would be dramatically more expensive computationally. As an example, I've indicated here that the cost of the model, or in other words, the time required to compute the solution, scales as Reynolds number cubed. So if you double the domain size, in other words, increasing the diameter by 2 and increasing the Reynolds number by 2, you're going to have 8 times the computational cost. For this reason, most people do not directly resolve the turbulence. So if you resolve all the scales of turbulence and the bulk flow in computational fluid dynamics, that's called direct numerical simulations, or DNS. You're going to want to remember that. That's one of the very generic things about CFD that you should know. DNS is the direct numerical simulations, meaning you're going to resolve all the scales of turbulence and the bulk flow. This is almost always done exclusively in research because of the cost and because of the relatively low benefit. Why do I say relatively low benefit? Well, because practically what you can do is create a model to describe turbulence, and that's almost always what is done. Okay? So what you do here is you only resolve the large eddies of turbulence, the very largest eddies, and the bulk flow. This is called large eddy simulation. It's much, much cheaper than DNS, but it's still quite expensive. Okay, so it's still mostly research applications or very specific locations where you want to know how the larger eddies resolve. For example, vibration and control rods in a nuclear reactor. Remember, we talked about how these control rods are 10 meters long and about a centimeter in diameter. Long, thin rods are prone to vibration when you have fluid moving past them because of the shedding vortices. And so a lot of the times they will do LES, or large eddy simulation, CFD, in order to determine what kind of vibration modes dominate in the fuel, to see if you're going to have problems cracking the fuel because they're vibrating so fast and humming, literally, inside that reactor. Okay? So a more common method is to solve for the average flows. So you take the Reynolds averaged value for these flows and apply the Navier-Stokes. Okay? So you can see here I have illustrated the average flow equations, okay, where the average is equal to the average with respect to some quantity time, which is very long, so the time averaged value of these Navier-Stokes equations. Note this is familiar, or should be. This is the calculus expression for an average, 1 over the domain times the integral over that domain of the expression gives you the average expression. Okay? So for each of the quantities we're interested in, we can take the Reynolds averaged quantity and use that to solve for our turbulent models. And that is a very common, very time-effective way of evaluating this. So this is really just 3 ways that we deal with turbulence. Okay? We can either do it directly with direct numerical simulations, DNS, or we can do large eddy simulations, or we can do Reynolds averaged Navier-Stokes. All 3 of those, you should know, there are 3 primary branches of resolving turbulence in computational fluid dynamics. And then finally, one last little bit that I wanted to cover was the explanation of how you can do some of these modeling. Okay? So let's take this. This is the Navier-Stokes equations, right? You guys are familiar with this by now. What we're going to do is we're going to do something similar to what we did when we first talked about turbulence. Remember, we talked about taking the overall velocity and breaking it up into the average velocity plus the local deviance from the average velocity. Okay? So in turbulent flow, you have a very, very large distribution of potential velocities as you go across the pipe. So we're going to assume that there's some average flow distribution. We're going to add some variance to that. And then we're going to define V bar as the average, V prime as the fluctuation. That's the terminology that I'll try to use. The average and the fluctuation, which is the variance from the average. Okay. Again, this is what we did with turbulent pipe flow. So we have here the continuity equation and the Navier-Stokes equation. What we're going to do is we're going to break this derivative of velocity with respect to time into the respective pieces of the average velocity and the variance of the velocity, the fluctuation. Okay? Then we're going to take the average of that value. And when we do that, notice we have this large average bar over the entire expression. The average of the variance is equal to what? Well, it's equal to 0, because if you average out the fluctuation, you will get the overall average. That's the point. This average is derived as the average value, and this fluctuation goes around that average to give you the average. So the average of the fluctuation is going to be 0, whereas the average of the average is simply the velocity average. Okay? So what we get then when we apply the average and that breakout into the average velocity and the fluctuation, we end up getting just the partial derivative of the average velocity with respect to the time. Now we have another velocity here that we need to resolve in that same way. Okay? So we have this gradient of the velocity, and using the same theory, we break that velocity up into the 2 parts, the average and the fluctuation, but the average of the fluctuation is 0 and the average of the average is the average. So we end up getting the Laplacian, or the second gradient, of the average velocity. Okay? However, we have one final velocity term that we need to resolve, this one here, the gradient of the velocity times the velocity, the 2 velocity vectors. That is much more difficult to resolve. So that's given down here. That is that term. And we're going to apply the same logic. We're going to break each of those velocities into the velocity average plus the velocity fluctuation, and then take an average combined of those. So we have the gradient of the overall average of the velocity plus the fluctuation times the velocity plus the fluctuation. Okay? And then using the distributive properties, we end up getting this expression, velocity average times velocity average plus 2 times velocity average times the velocity fluctuation plus the velocity fluctuation times the velocity fluctuation. Okay? So now we take the average of these. The average of the velocity average times the velocity average is equal to the average velocity times the average velocity. On the flip side, this velocity prime, the fluctuation times the average of the velocity fluctuation, is 0 still. So this term goes to 0. However, we now have a new term, which is the average of the velocity fluctuation times the velocity fluctuation. This is not necessarily equal to 0, as the average fluctuation was, because you now have a new expression where you multiply these together. We don't know what this is. This is a new term we haven't seen before. This is fairly easy to resolve. This is simply the gradient of the square of the average velocity. This, or I shouldn't say the square because this is actually vectors. So this is the gradient of the two vectors of the average velocity. This, however, is something more difficult. Okay? So when we take those and add them back in, we end up with the continuity equation is now, this should be equal to 0, the gradient of the average velocity. And then Navier-Stokes now becomes the gradient of the average velocity, or I'm sorry, the derivative with respect to time of the average velocity. The gradient of the average velocity times the average velocity. We have the gradient of the average pressure. We have the gravity term. We have this Laplacian of the average velocity, and then we have this new term here, the gradient of the average of the velocity fluctuation times the velocity fluctuation. So we basically have two equations with two unknowns, v average and p average, but we don't know this term here. And this is where the models come in. This represents the eddy terms. Because you'll notice all of these deal with the averages. So these are the terms that we are accustomed to dealing with. And this is the additional term that models all the eddies. Remember, the whole point of this is to figure out a way to explicitly model turbulent flows. And this does that. We just have to have a model that describes the eddies and the dissipations. And that's what we described before. This term right here is where we need to come up with models. This is the whole challenge of computational fluid dynamics. The rest of this is fairly simplistic and easy, relatively speaking. We can discretize averages. We can solve for averages just like we did in those two examples, no problem. But this term is the whole heart of the problem. We can explicitly model it, which is very complex, or we can come up with good models. Okay? And this term here is known as the Reynolds stress. It has units of stress, and it's usually modeled using this expression here, the kinematic viscosity, which is the turbulent viscosity, times the gradient of the average velocity. Okay? And that breaks it down to something very simple. And the standard model that we use for that is something called the K epsilon model. And you'll hear that a lot. I introduced that not so you can deeply understand it, but just so you can understand the whole challenge of computational fluid dynamics. So if you let me go over this again on the slide, we basically have these two equations and two unknowns in terms of the average velocities. But we don't know the Reynolds stress term, which again is the variance of the velocity times the variance of the velocity averaged. So we have to model that. And so if we can find good models for these terms, then we can have a good CFD model. Okay? Again, the standard model that is used for this is called the K epsilon model. And it is a model that approximates the behavior of these turbulent and eddy forces. Again, this refers to one of these methods where we'll explicitly solve for the large eddy simulation, but then we'll come up with models to express the turbulent behavior. So that is your quick run through in computational fluid dynamics, just scratching the surface to understand what's going on, what the challenge is, why it takes so long. If you guys have any questions, please come see me, email me, do whatever you can, do whatever you need to in order to make sure that you understand this material. Some of it will be on the test, and I will go over sample problems in the review on Friday.
best of luck, and I will talk to you guys later. Bye.